In determining whether a reaction is spontaneous, our observations show us that enthalpy change is not the only factor. Endothermic and exothermic reactions can both be spontaneous, so there must be another factor involved. And that other factor is called the entropy change. This is not something we would have predicted ahead of time. So we'll start by defining entropy. There's a technical definition, a more useful description that we will use, and a popular description that is somewhat ambiguous. Entropy is given the symbol S. Technically, entropy is a measure of the number of ways energy can be distributed within a system. This includes not only the energy of orbitals, but of modes of motion like vibrations and rotations within a molecule. You may encounter this statistical approach in a more advanced chemistry course. For our purposes, we will look at the number of ways a system can be arranged. We're making the assumption that the more ways a system can be arranged, the more ways energy can be distributed throughout that system. We'll see how this helps us understand the difference in entropy between the states of matter and between large and small molecules. You may be familiar with the popular definition of entropy being a measure of disorder. If that works for you, use it. But it's somewhat subjective, so we'll use the method of ways a system can be arranged. Let's think about a given material in the three states of matter. In the gas phase, the molecules are free to move about their container. There are many, many ways you can arrange those molecules. In the liquid state, we've put some restrictions on the way molecules can arrange. They need to be touching one another. By adding a restriction, we reduce the number of ways the molecules can arrange themselves. In the solid state, there are further restrictions. Not only are the molecules touching, but they're positioned in the crystal lattice to maximize the Coulombic interactions between them. The number of ways they can be arranged is smaller still. So, of the three states of matter, the molecules can be arranged the most number of ways in the gas phase, so the gas has the greatest or highest entropy. There are the fewest arrangements in the solid state, so the solid has the smallest or lowest entropy. It turns out that the entropy of a gas is much greater than the entropy of the liquid, which is somewhat greater than the entropy of the solid. The point is that changes in state during a process will result in entropy changes for the process, especially when a gas is produced or consumed.